Hi, welcome back to educator.com, and today's lesson in general chemistry is on the tools of quantitative chemistry. We're going to get introduced into how chemists go ahead and make measurements and the basic concepts and methods of performing everyday calculations. And so our first point in the lesson is going to be the SI units of measurement. Once we become familiar with the units of measurement, we'll then get into explaining how exactly good or bad your measurement was. And so this is done by something we call percent error and also standard deviation. We'll then get into a discussion of what we mean by precision versus accuracy. We'll then get into something a little more quantifiable, which is called significant figures and uncertainty, followed by the following. Identifying sig figs and then using these significant figures in calculations. We'll then get into a very important concept which is fundamental to all of the physical sciences, and this is called dimensional analysis, which is your use of what we call conversion factors for problem solving. Finally, we'll wrap up the lesson with a brief summary, followed by some sample problems. The SI units of measurement are what we call the International System of Units, and they are included as part of the metric system. And it's used in all parts of the world except the United States. So the basic unit, the basic SI unit for mass, of course, is going to be the kilogram. For length, it's going to be the meter, and for volume, it's going to be the liter. So kg again stands for kilogram. Okay, lowercase m is going to be abbreviating meter, and finally capital L is going to be symbolized for liter. Again, mass is going to be kilogram, length is going to be meter, and volume is going to be length is meter and volume is liter. All right. Now, when you make a measurement, how good or poor is it? And so how close was a measurement to an actual or already known value? So this is what we call percentage error. And percentage error is equal to the actual value, okay, minus the experimental value divided by the actual value. So actual value is the known value, and the experimental value is what you actually measured in an experiment. So what you measured. And of course, we always like to get as close as possible to the actual. And so to illustrate this very simple equation to use, suppose you weighed an object and recorded a mass of 86.2 grams. The known value is 97.9 grams. Calculate the percentage error. Okay, so known value is going to be actual, and what you recorded, this is our experimental value. And so the percent error, let's just plug everything into the equation, is going to be equal to the actual value, 97.9 grams, minus the experimental value of 86.2 grams, divided by the actual value, which was 97.9 grams. And all of this is going to be multiplied by 100 to get you your percentage error. The next statistic that we can also calculate is something called standard deviation. Sometimes when you repeat an experiment several times, it's useful to know how successful you were in reproducing your results. So if you did, for example, 10 trials of the same measurement, how well were you able to get the same measurement in each of the 10 trials? And so for our purposes, we want, of course, the standard deviation to be as low as possible. Standard deviation has the following equation. It's equal to the square root of all of these terms, where x is equal to basically each individual score. Okay, x bar is simply the average of all the x's. N is the number of values, or the number of trials. And summation, of course, means we're going to add up across all the values. Let's go ahead and illustrate the use of this equation. It looks like a lot, but it's really not too bad. You weighed an object 3 separate times with masses of 32.6, 31.8, and 34.1 milligrams. Calculate your standard deviation. All I'm going to do is set it up for us right now. And so the standard deviation is going to be equal to the square root of everything underneath it. Okay, so summation x minus x bar. Okay, so x is each score. Okay, 32 minus 6 minus the average. Okay, squared. And I'm going to put all this in brackets showing that we're going to add what's next. So plus, okay, 31.8 minus x bar, okay, squared. And then plus 34.1 minus x bar squared. Okay, and then close brackets. So that is what is meant by summation x minus x bar squared. And then divided by n minus 1, where n is going to be equal to 3 trials. So all of that divided by 3 minus 1. And so all we need then to finish this problem is x bar. Okay, so x bar is just your average of the 3 values. So that's just going to be 32.6 plus 31.8 plus 34.1, and all of that divided by 3, so giving you your average score. And that's standard deviation. All right, the next item is what we call precision and accuracy. Okay, so precision simply represents how well you were able to reproduce your results over several trials. And high levels of precision tend to support accountability and reliability. And so precision is going to be quantifiable by standard deviation. So measured by standard deviation. And again, you want as low a deviation as possible. So low standard deviation desirable. Okay, the word accuracy, however, represents how well you were able to measure a value in relation to an already known or published value from the literature. And of course, this is going to be measured by percent error. And once again, we want as low a percentage error as possible. So low percent error is also desirable. So a lot of people use the terms precision and accuracy interchangeably, but of course, as you just seen, they are not the same. Okay, one represents your ability to reproduce a certain measurement, and the second represents how well you were able to get to a known value. All right. The next item is very important whenever you make measurements, and this is called significant figures and uncertainty. Okay, so consider the following 2 rulers. So let me go ahead and draw one ruler, and I'm going to go ahead and draw a second ruler on the bottom. And now the difference is going to be their tick marks. Okay, 1, 2, 3, and then the next one is going to be the following. Okay, 1, excuse me. 1, okay, and 2. Let's go ahead and measure a piece of wood. That's this length right here, measured by green. I'm going to do the same thing with the other ruler. Just like that. All right. So one person, how would you measure the green stick with the above ruler? One person could say maybe 1.4 or cm, or another person could say 1.5 cm. It turns out that neither person is incorrect. Why? Because the 1 is what we know for sure. We know that a green object is longer than 1 for sure, 1 cm. And really, this last digit here, the 0.4 to 0.5, is really uncertain. It's the digit of uncertainty. And the digit of uncertainty is strictly up to you, the user. So up to person making the measurement. Because the ruler is so poor, the tick marks are so large, there's no way we can determine if it's 0.4 or 0.5. It is not provided by the tick marks on the ruler at all. However, when we go ahead and look at this ruler down here, we finally get the tick marks that's representative of the appropriate digit. And so here, one person could say 1.4, and because it looks like the green mark is right on the 0.4, one person could even say 1.40 cm. Another person could say 1.41 cm. Someone could say 1.42 cm. And someone could even say it's a little less, 1.39 cm. So it turns out that because of the tick marks, we can go one digit more. We can provide a better measurement. Okay, so better measurement due to what we call a higher level of precision. Okay, so again, it's a better measurement due to higher level of precision. And the rule of thumb is the following. Well, how many digits do you know how to record a measurement? You're always going to go one digit past whatever is given to you or whatever the limit is on the ruler. So go one digit past what is given by ruler or given by the ruler or instrument. Okay, so for example, when we go ahead and read a graduated cylinder, you always want to look at the bottom of the curve. You see how this water level is slightly curved? Okay, that's what you call the meniscus. And so you always want to look at the bottom of it. So what is provided to us here on this graduated cylinder? Well, okay, 50 is right here, milliliters. 51 milliliters is right there. Excuse me, 50 milliliters is right there, and 55 milliliters is right here. So we know that the meniscus is approximately 53 milliliters. And the graduated cylinder can tell us if it's 51, 52, or 53. So what the rule is we're going to go one digit past this. So we can say something like 53.0. We can say something like 53.1. We can even go under and say 52.9 milliliters or even 52.8 milliliters. Once again, you're going to go one digit past the last digit of certainty provided by the instrument. Now, when you make a measurement, it's important to always write it down with the correct number of these significant figures. So now, what are the significant figures? What are the rules for identifying them? And the rules for sig figs are the following. Okay, all non-zero digits are significant. A zero is significant when it is in between non-zero digits. And a zero is significant when at the end of a decimal number. And a zero is not significant when starting a decimal number. So let's take a look at a couple examples. So all non-zero digits are significant. So for example, 562, we have a grand total of 3 sig figs because none of them are zeros. A zero is significant when it is in between non-zero digits. So something like 501. Okay, this is 3 sig figs. The zero counts because it's in between non-zero digits. 5001, both zeros count because they are in between non-zero digits. Okay, how about 50010? Okay, only the 2 zeros count here because they're in between non-zero digits. This last zero here does not count. And so we only have 4 sig figs here. A zero is significant when at the end of a decimal number. So for example, 500 dot. Okay, 500.0. Turns out that in 500 dot, all of these are significant. The zeros come at the end of a decimal number. Here, 500.0, these are all significant because they come at the end of a decimal number. A zero is not significant when starting a decimal number. So for example, 0.00321, the 2 zeros do not count here because they start a decimal. So we only have 3 significant figures here. However, 0.003210, okay, these do not count at all. However, You see the 0 here that comes at the end of a decimal number, so this definitely does count, and we have a grand total of 4 significant figures. Okay, now when we use significant figures in calculations, we have to learn how to incorporate the rules now. So for multiplication and division, the answer will have the same number of sig figs as the fewest number of sig figs present. For addition and subtraction, the answer will have the same number of decimal places as the fewest number of decimal places present. So for example, 0.321 times 0.57, okay, we are going to get an answer that is only 2 sig figs. Why? Because here in 0.321 you have 3 sig figs, and here in 0.57 you have 2 sig figs. Now, when we do the addition and subtraction with the same numbers, 0.321 minus 0.57, you see, now we go by digits after the decimal places. Here there's 3 digits after the decimal, here there's 2. And so our answer is going to have 2 digits after the decimal. Okay, and finally, when you have mixed operations, you never want to round until the end, and you want to carry all digits through. All right, so now that we've talked about significant figures, let's go ahead and discuss what we mean by dimensional analysis. And dimensional analysis utilizes the following. It utilizes ratios of different units that we call conversion factors to convert from one unit to another. And so if you want to go, for example, from unit A to unit B, how do we go ahead and do that? The general format is the following. We're going to take unit A, we're going to multiply by this ratio, something over something. That's going to go ahead and give me unit B. Okay, so unit A goes downstairs to get canceled, and unit B goes upstairs to get carried through to the final answer. And so this ratio right here of unit B to unit A, that is what you call your conversion factor. Let's go ahead and look at a couple of examples. Okay, there are 4 laps in 1 mile. How many miles are in 17 laps? So we're going to say 17 laps, okay, times something over something, and that's going to give us our answer in units of miles, which is what the question is asking for. So I start with laps, but I want to cancel it, so it's going to go downstairs to get canceled, and miles goes upstairs to get carried through to the final answer. The conversion factor is actually given to us in the problem because they state that 4 laps is equal to 1 mile. So this is then 1 mile on top and 4 laps on the bottom, and we're going to get 4.25 miles for your answer. Now, this is going to round to 4.3 miles, and let me tell you why. Okay, 17 laps, you have 2 sig figs. However, for conversion factors, we are assuming that a conversion factor are what we call exact numbers. That is, they have infinite precision. They have infinite significant figures. There is no uncertainty. And so you're going to ignore conversion factors for sig fig purposes. Once again, you're going to ignore conversion factors for sig fig purposes. All right, let's go ahead and look at one last example here on dimensional analysis. 1 pound is 454 grams. How many grams are in 1.22 pounds? Okay, so 1.22 pounds times something over something is going to give us our answer in grams. Okay, so I want to cancel pounds, so that goes downstairs. I want to keep grams, and that's going to go upstairs. You're told that 1 pound is 454 grams. And so 1 pound on the bottom and 454 grams on top. And that's going to give us an answer of 553.88 grams. And so here we have 3 sig figs. And so our answer is going to round to 554 grams. All right, so that again, that's what we call dimensional analysis. And it's important to really master this because we are going to be using this incredibly heavily throughout all our lessons in general chemistry. Okay, One last example then. Suppose a diaper costs 25 cents. You have a newborn who goes through about 14 diapers a day. How much is spent on diapers in 1 week? Okay, so suppose you have a diaper costing 25 cents. So that's actually a statement already. And we are told that 25 cents costs each diaper. So 25 cents per diaper. Okay, so we're trying to multiply through and cancel units. The other item we see here that has diapers is 14 diapers a day. So that's another ratio. So 14 diapers goes upstairs to get canceled, and then 1 day on the bottom. And finally, I want to get my answer into week, right? Or dollars per week. And so this is going to now be 7 days on top to get canceled, divided by 1 week on the bottom. And when all is said and done, you're going to get an answer of $24.50 per week to be spent on diapers. So as you can see, the reason why we're doing these examples that are not chemistry yet is to show you that dimensional analysis, which we use in chemistry and the physical sciences, can actually be very easily applied to everyday life. Now, the next type of dimensional analysis deals with unit conversion. You know, you've heard of terms like centi and milli and kilo before. But how do you convert between the three? We're going to learn that dimensional analysis is all behind this, converting between units. You should ask your chemistry instructor which units you actually have to know. But let me go ahead and just point out a few. Okay, so mega is 10 to the 6. Kilo is 10 to the 3rd. Okay, deci is 10 to the -1. Centi is 10 to the -2. Milli means 10 to the -3. Micro is 10 to the -6, and nano is 10 to the -9. So once again, please ask your instructor if you have to memorize any of these, if at all, or if they're going to be given to you. Well, now that we have been introduced to these prefixes and what they mean, let's go ahead and see how we can use them in calculations. For example, 500 milligrams is equal to how many kilograms? And what I always like to say is that sometimes it helps to convert to the base unit first. And what I mean by the base unit is that it has no prefixes. In other words, let's get to the unit with no prefixes first. So first step is to go from milligrams to regular grams, then on to kilograms. So this is going to be a two-step process. Okay, so 500 mg. Let's go ahead and set it up, times something over something. Okay, so the first step is to get G. So G goes upstairs, mg goes downstairs to get canceled. Once I'm in G, now I can go to kg. So times something over something, and that's going to give us our answer in units of kg. So you see K is up, you see that G is upstairs here, so it's going to go downstairs to get canceled, and kg goes upstairs to get carried through to the final answer. Okay, now, what numbers do we put in and where? Well, the rule is the following. For the prefix multipliers like kilo and milli, you put the multiplier with the base unit. Okay, so put multiplier with the base unit. Once again, you should put the multiplier with the base unit. And so for milli stands for 10 to the -3. And that's going to go with the base unit here, 10 to the -3 on top, 1 on the bottom. Kilo stands for 10 to the 3rd, and that's going to go with the base unit. So 1 goes to kg, and 10 to the 3 is going to go to the g. Once again, you always put the multiplier with the base unit, everyone. Okay, and then you get your answer in kilograms. Let's go ahead and do a last one. So this is centimeters to micrometers. So the first step is to go from centimeters to regular meters, and then from regular meters on to micrometers. Okay, so 34.1 centimeters times something over something is going to give me my answer in meters. Okay, cm goes downstairs to get canceled, m goes on top to get carried through to the final answer. Once I'm in meters, I can then go on and get micrometers. So times something over something, that's going to give me my answer in micrometers. Okay, so you see that m is on top, So it's got to go downstairs to get canceled, and then micrometers goes upstairs to get carried through to the final answer. When we look up the prefix for centi, centi stands for 10 to the negative 2. So that goes with the prefix less unit. So 10 to the negative 2 on top, 1 on the bottom. And when we look up the prefix for multiplier for micro, it's 10 to the minus 6. And that goes downstairs with meters and 1 on top. And that's going to get your answer in units of micrometers. So, to summarize, when you perform measurements, you want to gauge how well you are doing. And we can do this by percentage error calculation, which again is going to tell us a little about your accuracy. And we can also calculate what's called the standard deviation, and that's going to tell us of how precise you were. We also learned the concept of significant figures, and significant figures is related to precision. Finally, we learned a very fundamental concept in all of the physical sciences, which is dimensional analysis, which follows the same basic pattern where we can go from unit A to unit B using a conversion factor. All right, so there's our summary, and now let's go ahead and tackle some sample problems. An intramolecular medication is given at a dosage of 5.00 milligrams per medication of body weight, per kilogram of body weight. If you give 0.425 grams of medication to a patient, what is the patient's weight in pounds? All right, so the 0.425 grams of medication is here, and somehow we want to go from grams of medication to whatever the question is asking for, which is pounds of body weight. Okay, in addition, we see in the first sentence that we have a statement here that 5 milligrams of medication are given per kilogram of body weight. Well, that represents a very nice ratio of 5.00 mg of medication for every kg of body weight. And that's our conversion factor. Well, this unit is 5 milligrams of medication, and we're given 0.425 grams of medication. So we got to get the 0.425 grams of medication in the milligrams first. So 0.425 grams of medication times something over something is going to give us our answer in units of milligrams of medication. Okay, so milligrams goes upstairs and G goes downstairs. When we look up the prefix for milli, it's 10 to the negative 3. That goes with the prefix less unit on the bottom and then 1 on top. And that's going to give us milligrams of medication, which is going to be 425. We can then take the 425 milligrams of medication, multiply it by something over something, and that's going to give us our answer in units of body weight. In kilograms of body weight, excuse me. And so mg is going to go on the bottom, kg is going to go on the top. And we know that from the first sentence, it's 1 kg for every 5.00 mg. Finally, we can then take our kilogram of body weight and we can go to pounds of body weight. And we do that from the conversion factor, where 1 kilogram is equal to approximately 2.20 pounds. So we're going to take kilograms of weight, multiply it by something over something, and that's going to give us our answer in pounds. So pounds goes upstairs, kg go downstairs, and just 2.20 divided by 1. And when all is said and done, we should get an answer of 187 pounds using the correct number of sig figs. All right, so that's our lesson from General Chemistry on quantitative tools. And I want to thank you for your attention, and I'll see you next time on educator.com.